Hi, my name is Arian Jadbabie. I'm a freshly minted PhD in physics from Caltech, and I'm here to talk to you today about some of my research in graduate school titled Bringing Imbalance to the Universe. And because this is a Caltech science journey, I'm actually going to begin by telling you a little bit of what inspired me on my journey into physics. When I was a young child, I was really mesmerized by spinning things. And you can see here, for example, a ceiling fan and me as a little kid. And I think this was probably very convenient for my parents because they could just take me to a fan and it would not only calm me down, but it would almost cast me under a trance. And I would sort of proclaim, it's spinning, it's spinning. And I actually do still work with spinning things today. They don't quite look like ceiling fans. They look like cold rotating molecules. And I also don't look like this anymore. I look a little older. But at the end of the day, we use these cold rotating molecules to learn about very deep fundamental questions in physics related to the Big Bang, the origins of our universe, and how we came to be here today. And that's what I'm going to talk to you today about in this talk. Now, I'm going to start with a visit to the museum. And this is something that was a really impactful moment for me as a young kid. This is a picture of me when I was about 6 or 7 years old. And one day, my parents and I, we took a trip down to Washington, D.C., where we went to the Smithsonian's National Air and Space Museum. And the Smithsonian Museum has a really, really large IMAX screen. And you can imagine when you're really tiny, the screen looks even bigger. When we were there, we got to see an IMAX movie that had a really important impression on me as a kid growing up. And that was this movie here called Cosmic Voyage. It's from 1996. It's narrated by no one else than Morgan Freeman. And I'm going to show you a small clip from this sort of IMAX movie that had a really important impact on me as a kid. So we begin zoomed out looking at the whole universe, and immediately the camera zooms right in. And I absolutely love any of these kind of zoom out or zoom in videos because they really give you some context for where we are in this universe. Now, to some people, this is a bit dizzying, right? How are we so tiny and the universe so large? But what's incredible to me is that as we zoom in through all these scales can be connected to what we experience as humans. We can learn about the very big, or as you can see here, as we zoom into a water droplet, the very small. As we go further beyond the amoeba and the DNA, we get to atoms, and we get to what's inside the atoms. We see the nucleus of the atom, and then even further. And this is what captivated me as a kid. What happens if you keep zooming in, if you keep zooming out? Where do you end up? And now for those of you who can, I would recommend scanning this QR code. This gives you access to an interactive sort of powers of 10 zoom in, zoom out website that's really sort of fascinating and fun to play with. Now, physics really should be thought of as the study of scale, I think. Here I found a diagram that shows you kind of in a picture what I just showed you in a movie. Now, as you go up and to the right in this diagram, we go to larger and larger scales. Each rung of the ladder here represents an increasing factor of 10. So 10 to the 2 zeros after the decimal place, while 10 to the minus 2 is 2 zeros before the decimal place. And you can think of us as humans kind of sitting where the decimal place is. As we go bigger and bigger, we get to larger and larger scales of the Earth, the solar system, the nearest star, galaxies, even the size of the whole universe, which is about 26 zeros after the decimal place in terms of meters. Meanwhile, as we go to smaller and smaller scales, we find we go from biology to chemistry to physics, and we end up at the nucleus, which we saw in the previous slide, or we end up even smaller, which is the constituents of the nucleus, quarks. And what's incredible to me, the story of physics is the story that all of these scales are connected to each other. And not just the scales of size, but scales of temperature, scales of energy, velocity, speed, time. All of these scales are kind of interrelated, and what we learn about in physics is how to connect with these different scales to our human scale. So how do we learn about these scales? What business do I have knowing about the nucleus of an atom or something the size of a galaxy if I'm just the size of a human? Well, what we do is we bring these scales into our perception. So at the large scale, we can learn about the universe through observations. I have here a picture of a telescope at the Palomar Observatory. And also you might have heard of the James Webb Telescope, which is actually in space. And we get these beautiful photos of the universe, and the important thing about these large-scale sort of observations is we don't get to choose necessarily when the experiments happen. We just receive images from space as they happen, so we have to be always looking. Meanwhile, at the small scale, we can learn about sort of what we're made of with experiments, where we choose when and what happens. At the largest of these experiments, we have things like particle colliders. An example of this is the Large Hadron Collider, with about a 27-kilometer circumference that we sort of move particles around near the speed of light and smash them together. At smaller scales, we have the sort of experiments that I'm used to working on. These are tabletop experiments, often involving lasers, which are very sort of precise and allow us to make very precise measurements of sort of fundamental physics. And this is how we can learn about what are we made of, what's even smaller than, say, the atom or the nucleus. All of these experiments at these different scales make me feel like this kind of painting over here. That could be you, that could be me. We're here in our ordinary sort of world, but when we peek through it, when we peek either at the stars or when we zoom in to sort of what we're made of, we see that we've uncovered sort of the inner workings of what's going on in the universe. And it's always much more complicated than we can imagine, but it's really a privilege, I think, to be able to explore these different scales and to see how they're all connected underneath. This particular image is known as the Flammarion engraving. It was first published in 1888. The author of this, a man named Flammarion, sort of put it in a paper that he wrote, a book that he wrote on atmospheric science. And the caption for this image is very telling. The caption describes the point where the sky and the earth meet. And if you think of our position as humans in scale, we're really kind of in between, if you will, the sky and the heavens, which are the stars at kind of the large scale, and the molecules, atoms, and the nuclei, which is kind of the constituents of the earth. And I think what's really incredible is being able to sort of see the magic that's going on at all these scales. Here's a picture of me in my youth trying to grapple with sort of magic. And now here's a picture of me now that I'm older doing science outreach here in LA at the City of STEM Fair. For me, this is a way of sort of sharing the magic with others. And I think this is what's really incredible about science. Sometimes it's really magical, but it's magic that we're allowed to share the secret with. And in fact, the most incredible I feel is when I'm able to share this kind of magic with others. So a little bit about my background and where I came from. I was born in Iran, which is all the way over here in the other side of the world. That's me as a little kid. And when I was about 2 years of age, me, my mom, and my dad, we immigrated to the United States. That's a picture of me and my lovely mother. And I was able to then grow up in the US, and that's the picture of me on the first day of second grade, excited to go learn about the universe. So now I'll tell you a little bit about my education. For elementary school, I went to Beecher Road School. That's in Woodbridge, Connecticut. And I had a lot of sort of teachers there that influenced me. For middle and high school, I went to the Amity Regional School District. Now this here is a picture of the Amity debate team. It may seem odd that I'm talking to you about debate in a physics talk, but for me, debate was one of the ways that I was able to practice getting comfortable communicating and sharing ideas at a large scale. And it's probably some of the reason why I'm here talking to you right now. I also want to thank my English teacher in high school, Marissa Smith, who had a really big impact on me and encouraged me to think about big fundamental questions, not just related to physics, but philosophy, and to see how all of these questions are kind of related at the end of the day. Moving on, I went to undergrad at Washington University in St. Louis. And there, I was really fortunate to meet Cater Murch, a professor who sort of mentored me near the end of my time there. And without his sort of mentorship, I might not even have gotten here to Caltech today. Now, when I applied to Caltech, I didn't get in at first, and I want this to be a lesson that if you want something, keep trying. Instead, what I did in my year after my undergrad is I was in the Science Undergraduate Laboratory Internship Program run by the Department of Energy. And I worked at Brookhaven National Lab and Lawrence Berkeley National Lab on different projects. And these projects kind of made me into a better scientist, exposed me to more people, exposed me to more ideas. And then finally, when I reapplied to Caltech after a year of these internships, I was accepted, and I've done my PhD here at Caltech, and I recently graduated just this past couple of weeks. Now, what are some of the influences that I have in my life? Well, the big influence for me is the Magic School Bus. And if you're not familiar with it, the story of the Magic School Bus is we have this eccentric sort of teacher, Miss Frizzle, and she takes her students on various field trips using this school bus that can sort of transform into anything. You can see here in this image, the school bus is transformed into a rocket ship. And the students are now exploring the outer reaches of the solar system and of space. Sometimes the Magic School Bus took me to the age of the dinosaurs, the depths of the sea, the complications of the jungle. And for me, as a kid, this was unbelievable, an opportunity to kind of explore all these different places, all these different scales, and to learn kind of about the machinery of what's going on. Another big influence in my life was Star Wars, and you can see me here fighting off the forces of evil. For me, Star Wars was another way of exploring a whole world, going into space, as if I didn't have the constraints that I have in today's society, and I can fly around seeing different planets. And another thing that was really important for me is Star Wars wasn't just about the science. It was also about sort of the emotions, the feelings, and kind of this mystical aspect of the universe. And I think that had an impact on me as well. Now finally, I need to talk to you about a video game I played a lot of as a kid called Civilization. And it's a video game about history. And while once again it may seem odd that I'm talking to you about history at a physics talk, it was really crucial for me to sort of get a context for thinking about big pictures of human history, thinking about ideas that have proliferated through history, and the connections of science to history, politics, and philosophy. And this actually played a role in getting me interested in debate as well. So these influences were a really sort of big impact on me growing up as a kid and pushed me towards thinking about fundamental physics. Now I want to tell you a little about an 8th grade project I had, and the prompt of this project was to explain an element to some aliens. So here I am with my cube of my element, and the aliens show up, and we have to explain to them what this element is as if they didn't know. My element was thulium. I actually was able to find sort of this original document. And you can see here from my title slide that I used to think word art was all the craze. Now, what's interesting for me is that even though my title is all about thulium, if you look at the actual report, most of the report, over a majority, I wrote not about my element. Instead, most of my report was a background. I had to tell these aliens, after all, what are elements in general? What are atoms? What are atoms made of? What are those made of? These are the sort of questions that sort of drove me as a kid. And in fact, when I handed this report in, I didn't really get a perfect grade because the point of the report was to talk about the element, not the background. But I gained something much more valuable, which was I gained a curiosity. I gained an interest in sort of fundamental physics, and I gained an exposure to these very deep questions about what we're made of. So now I'll tell you what I learned. What are we made of? Well, we're made of matter, and most of matter comes in the form of atoms. This is a sort of schematic of the simplest possible atom, the hydrogen atom. The hydrogen atom is extremely abundant. It's actually most of the sort of gas that we observe in the universe. It's part of the constituents of stars and galaxies, and hydrogen, amongst other atoms, forms the building blocks of life. The hydrogen atom can sort of be decomposed into two parts. We have, at the center, a positively charged proton, which consists of the nucleus. And then we have the electron. And now you may have seen the electron as a particle, but really we should think of it like as kind of a wave. It's in this cloud, and it has a chance of being found anywhere in this cloud. And I want to point out the electron is actually much, much smaller, about 2,000 times smaller than the proton. So we have this big, heavy proton in the middle, and this small, light electron flying around. Now, we can build more and more complicated matter, either by adding more electrons, in which case sort of the electrons form these really fascinating shapes. These are called atomic orbitals, and these happen at the scale of about 10 to the minus 10 meters. Or we can add more protons and neutrons. And in fact, sometimes we often do both, add electrons and protons and neutrons. When we add protons as well as neutrons, which are neutral sort of partners of the proton, we get sort of multiple particles stuck together in the nucleus. And these particles are held together by the strong nuclear force. And here's a sort of schematic of a nucleus with the protons and the neutrons. And they're made of even smaller particles called quarks, which bind to each other with this strong nuclear force. Now, because the strong force is pretty strong, after all, its name implies, the nucleus exists on a scale that's about 10 to the minus 15 meters. That's 5 orders of magnitude, 5 factors of 10, smaller than the scale that the electrons occupy. Now I'm going to talk to you about where these atoms and where this matter came from. And what's really incredible is that we can sit down and kind of, as physicists, talk about the history of the universe. Now, on the bottom axis, I'm plotting the age of the universe, going from left to right. And as you may have heard, we begin things off with the Big Bang. Now, you should think of the Big Bang not as an explosion somewhere in space, but as an explosion of all of space. What we think of is that the universe, long time ago, was compactified into a single point. And we sort of believe this from astronomical observations. And this single point at one sort of time, which we'll call 0, exploded out into what we call the Big Bang. Now, in the beginning, we have a series of sort of the gravity being as strong as the other forces. And this is kind of a complicated period that we don't really know much about, and it's hard to understand. But we think that there was a period of rapid inflation where the universe ballooned in size over a really, really small time period. And that's shown here by kind of this tube expanding out. The universe is always expanding, but during inflation, it expanded really rapidly. At the end of inflation, which ended about 10 to the minus 32 seconds after the Big Bang, a really, really short amount of time, the universe is the size of about a grain of sand. Now afterwards, the universe begins to cool as it expands further and further. And eventually, the universe cools down to the point where we get the formation of protons. Now, between the end of inflation and the formation of protons, a lot of interesting physics happens that I don't have time to talk about today, and there's a lot of really open-ended questions about what exactly was going on. We think that the fundamental forces, which at the beginning were unified, kind of split up, and we got different forces like electricity and magnetism or the nuclear forces. Now, after about a microsecond, when we get protons, those positively charged particles that make up the nucleus, the universe continues to expand and cool further. And eventually, we get to the point where these protons and these neutrons can come together and start fusing to form nuclei. And so we get not only the nucleus of a hydrogen atom, but we get the nucleus of bigger atoms like helium or lithium. And then by looking at the abundance of these sort of nuclei, after the period of sort of 0.01 seconds to 3 minutes, where we produce these nuclei, we can compare our theoretical models to sort of our experimental observations. And this gives us a lot of sort of strength in our belief of kind of this story that I'm showing you. Now, after 3 minutes, the universe begins to expand and cool further and further. And eventually, after 380,000 years, the universe cools down to the point where the first atoms can form. And this is not just the first atoms, but really you should think of it as the first light. When the universe is hot, the light particles can't sort of get out. The universe is opaque. They keep bouncing into different particles. But when we form atoms, atoms are kind of picky about the light that they want to talk to. And so most of the light in the universe at that point was free to kind of flow out and travel. And actually today we're able to observe this cosmic microwave background. It's kind of like the afterglow of the Big Bang. And it also gives us a lot of information about sort of what we think was happening over the history of the universe. For some context, at this point, the universe is already 840 times larger than the Milky Way galaxy. So the expansion sort of over time has been expanding the universe further and further apart. And now I'm going to fast forward a lot more time. We have a period of time where there's no stars, we just have gas. And eventually this gas comes together under the force of its own gravity, and the first stars and galaxies form. And then the astronomers take over and they tell us about the story of how the galaxies and how the structures of the universe formed and how we ended up to where we are today. But as physicists, I'm really interested in kind of those first 3 minutes, because that's really where so much of our universe came to be. Now, this picture that I've shown you, I mentioned there are many open questions, and now I'm going to tell you about some of the things we don't understand about this picture. So one of the very simple questions that we can ask of ourselves is, what is the universe made of? And the answer to this question actually shows a lot of sort of the gaps in our current understanding of the universe. You might, for example, imagine making a pie chart of what the universe is made of. And in this pie chart, you would find that ordinary matter, the atoms that sort of make us up, is a very small fraction of the overall energy we see in the universe, maybe 5%. The remaining constituents of the universe we call dark matter and dark energy, and we learn about these through astronomical observations. Dark matter we learn about by looking at the afterglow of the Big Bang, the large-scale structure of galaxies and matter in the universe, the rotation structure of galaxies as well. And dark matter, you should really think of it as transparent matter. It doesn't interact with any of the forces that we're familiar with, electricity, the nuclear forces, but it does interact with gravity. And we're able to see its pull on sort of galaxies and other structures in the universe. Now, this gravitational interaction, because it's so weak, it makes it hard to study dark matter. And there's a lot of experiments, which I don't have time to talk about, that are looking for evidence of dark matter here on Earth. Dark energy, meanwhile, is even less well understood, and basically it arises from the fact that the expansion of the universe that I showed you earlier seems to be accelerating over the last couple of billions of years. And this accelerating expansion of the universe, we chalk it up to this energy in every sort of empty cube of space called dark energy. Now, if you imagine the constituents of the universe as jelly beans in a jar, you'd find that dark energy and dark matter can comprise most of this jar. And the sort of lighter jelly beans, the colored jelly beans, which we're made of, are a very small fraction. But even that small fraction has mysteries, and that's what I'm going to talk to you about today. If you look at these jelly beans, you see that we're made of matter, and all the galaxies are made of matter, but not something we call antimatter. Now, you might say, well, antimatter, isn't that science fiction? But actually, it's very real, and I'm going to talk to you about it next. So now, we might ask ourselves, well, what is antimatter? And to refresh your memory, here's what we said matter was. It's like things like the hydrogen atom. Now, to get antimatter, you just reverse all of the electric charges. So instead of a positively charged proton, antimatter has a negatively charged antiproton. And instead of a negatively charged electron, we have a positively charged anti-electron. Just as an atom is held together by electromagnetic forces, so too is antimatter held together by electromagnetic forces. But it looks kind of like the charge opposite. Antimatter is only produced in exotic processes, things like radioactive decay, but we can detect it, so we do know it exists. It was actually first detected here at Caltech in the 1930s. Antimatter, we think, comprises about 0% of the observable universe. And we know this because if there were a galaxy made of antimatter, at the interface between that galaxy and our galaxy, we would see a huge signal from all of the matter and antimatter annihilating. And that's because when matter and antimatter come into contact, they actually turn into energy. They annihilate, this is what we call it as physicists, and give off sort of a lot of light. And we would see this sort of signal, and this would tell us that there's an antimatter galaxy out there. Because we don't see these kind of annihilation signals, we think that most of the universe is actually made up of matter. So now we see that there's this kind of open question. Why are we made of matter and not antimatter? There's a symmetry kind of between these two things that's broken. And now we can ask ourselves about symmetry in nature. Is nature symmetric, and should our models be symmetric? For example, some things in nature, like the sunflower, have a radial or rotational symmetry, where if you rotate it, it looks the same. Other things have a mirror symmetry, like this butterfly. If you mirror it across the center, the butterfly looks the same. Some things have more complicated symmetries, like spiral symmetries of this broccoli or this galaxy. And some things in nature just aren't symmetric. And that's okay too, because they serve really important functions. Now, what's interesting for us is that we also rely on asymmetry in order to exist. And this is the imbalance that I talked about in my title. So we need this imbalance. If we imagine starting from the Big Bang, let's assume we lived in a symmetric universe. In such a symmetric universe, we have equal amounts of matter and antimatter, shown here kind of with these bars. And when matter and antimatter come into contact, they annihilate. And when they annihilate, we're left with no matter and no antimatter and just light. And we can't get the sort of universe that we're used to today, which is made up of atoms and sort of ordinary matter. So instead, as physicists, we think that there existed some new particle or some new force, I've denoted here with an X, that could have generated a slight asymmetry of matter and antimatter. If you look here, the matter bar, M, is slightly higher than the antimatter bar, A. And when these two annihilate, we have a little bit of matter left over, and that little bit of matter actually goes on to become sort of the galaxies that we see today, the Earth that we see today, and the atoms that make up all of us. So we really need this imbalance in order for the universe to exist as we observe it today. Now, it turns out we haven't found the source of this asymmetry, and we can look for it in our science experiments. Can we discover the origins of the matter and antimatter imbalance? So we have this imbalance, and it turns out that this imbalance has to result from asymmetric laws of physics. And the asymmetric laws of physics can have other experimental signatures at the scales that we can probe and study. So let's start again with the atom that we talked about earlier. Now, if you zoom in on the atom, you might be able to say, look and try to understand the electron. And you may have seen the electron represented as kind of like a spherical particle in your classes or in popular media. But actually, this asymmetry of the matter-antimatter imbalance could result from laws of physics that would also cause the electron to be asymmetric. The electron would sort of have an oblong shape, a deviation from spherical symmetry. In science, we call this as the electron having an electric dipole moment. And in my research, we look for the electric dipole moments of fundamental particles like the electron to learn about the asymmetries that exist in our universe. So now, while I showed you how this asymmetry can manifest in the electron and inside an atom, we actually look for the asymmetry inside molecules. And I'll tell you a little bit about how that works. So the first thing is, how do you even detect the asymmetry of the electron's shape, or as we call in physics, the electric dipole moment? Well, you apply an electric field and you watch as the electron rotates, does the rotation have a wobble? And does that wobble depend on the direction that the electric field points in? And this is the key to kind of seeing if there's an asymmetry in the electron's shape. Now, what we do is we apply these electric fields not in the lab, but actually inside a molecule. It turns out that molecules have very large internal fields that make them sensitive to these asymmetries. So here's a picture of our lab, and inside our experiment, we might have these polar molecules that have a positive and negative charge, and so they create an internal electric field. And this internal electric field is actually really like 100,000 times stronger than what we can artificially produce in the lab. So it makes these molecules a really powerful tool. If you think of the electron's shape as sort of an antenna for the interactions with new particles and forces, then the molecule is like our amplifier. It boosts this new physics signal to a scale where we can measure it in the lab. Now, another really important thing about molecules is that we can align them in the lab by applying an electric field. And this makes the molecules polarizable. By applying a very small electric field in the lab, we're able to orient the molecules and access the sort of full magnitude of their internal field. Now, finally, this field has a lot of room to grow. So far, measurements of the electron's shape indicate no deviations from a sort of spherical symmetry. But the imbalance between matter and antimatter in the universe tells us that if we keep looking, we should find some evidence for the asymmetry of nature inside the electron. So I want to give you some context for my PhD. This is what the lab looked like in February of 2018. As you can see, it's pretty empty, although we have a lot of room to grow in. And I want to draw your attention to the orange box in the corner. That orange box is going to become sort of the science experiment that I worked with in my PhD. Now this is the same sort of angle. This is a panoramic of the lab today. And you can see it's full of science, full of wires and all kinds of different contraptions and apparatuses. And it's a really fun place to be in. That orange box is actually there in the right side in the corner, although you can't really see it because it's hidden by all of the wires and science that we've installed. Now, in our experiments, we want to produce these molecules at very, very low temperatures. And for that, we use an apparatus like this called a cryogenic buffer gas beam source. And this was built in collaboration with my coworker, Nick Pilgrim, who I want to give a shout out to. Now, how does this work? Well, we want to produce our molecules at really cold temperatures. And so the first thing we do is we have to insulate our molecules from the outside world. The outside world is given here in this kind of orange chamber, and it's at what we call in science 300 Kelvin. And Kelvin is the scientific term for temperature. 300 Kelvin corresponds to about room temperature. And as we go further and further, we get sort of stages. Really, these are shields to insulate our molecules that are at colder temperatures. 50 Kelvin is about minus 250 degrees Celsius colder than room temperature. So already we're getting very cold. And in the center, we're at 4 Kelvin. And 4 Kelvin is about minus 269 Celsius, or in Fahrenheit, something around minus 450 Fahrenheit. In terms of Kelvin, it's about 4 degrees above absolute zero, which is the coldest anything can get. And so once we have our sort of experiment at a cold temperature, you can see here we have to put super insulation to kind of insulate it against the heat from the outside. And now I want to point out this thing in the middle, which is our buffer gas cell. This cell is at 4 Kelvin, and we flow in cold helium gas constantly through this fill line. And as we flow in the cold helium gas, we stick a solid target on the backside here, this target plate, and we vaporize this target with a pulsed laser. And this creates a plasma that's at temperatures of over 1,000 degrees. But quickly, the plasma that we create interacts with the cold helium gas, and after about a millisecond, which is a really short period of time, we end up with cold molecules that are also cooled down to 4 Kelvin. And this technique is really versatile because you can put a hole in your copper box, and now you have a beam of molecules streaming out. We can study the molecules using kind of windows that we shine laser beams through, and when we look at the molecule quantity, we see how much the laser beam is kind of getting attenuated. In other words, we look at the shadow that the molecules cast on the laser, and that tells us how many molecules we've made. We also fill this sort of area up with charcoal. It turns out at low temperatures, charcoal is really good at pumping out helium, which we need because we're constantly flowing helium into our experiment. And then the molecule beam kind of exits this way and goes downstream into other vacuum chambers where we can perform further experiments and further manipulations. Now I'm going to give you a quick speed run of the rest of what I did in my PhD. So the first thing was learn how to make lots of these molecules. And I told you we make these molecules by vaporizing a solid target in the presence of cold helium gas. But one of the things that we learned is if we come in with a laser beam and excite sort of atoms that haven't yet reacted to form molecules, we can actually make an order of magnitude more molecules. We basically drive chemical reactions using this laser. And as you can see here on this plot, the orange trace shows that when we have the laser beam on, we make about 10 to the 11 molecules every time we sort of run our experiment. So okay, with lots of molecules made, the next step is to characterize and understand the molecules. After all, if we want to make a measurement looking for new physics, we have to first understand the existing physics. And we did this, and you can see here very clearly, this is a plot of our molecules' energy shifts as a function of the electric field that we apply on the x-axis. And you can see as we apply the electric field, we really do polarize this molecule, and we obtain these 3 orientations that I told you about, pointing up, sideways, and down. And that's really important for these experiments that we want to perform. And the final thing is to demonstrate sort of quantum control and manipulation of the molecule. After all, we want to look at how the electron behaves as it experiences the internal field of the molecule, and we want to look at exactly how the electron is spinning. And this is kind of what I've shown here in this plot. This is sort of our evidence that we are really able to apply coherent quantum control and watch this electron spin around and study its properties. Now, the final thing, which is ongoing, is to build and commission a science chamber to actually do these precise measurements. A lot of the stuff I've talked to you about previously happened in a prototype chamber. This is kind of what the experiment is looking like today. You can see that orange source in the center, all the mirrors we use to steer our laser beams in, and on the right you can see this big metal box. That metal box is our beamline where the molecules will fly through, and when the molecules fly through there, we'll shine them laser beams on them, we'll apply electric and magnetic fields to them, and we'll really study sort of how does the molecule behave in the presence of these fields to look for small asymmetries that could result from the shape of the electron being asymmetric. That metal box, by the way, is a bunch of magnetic shielding. Our experiment is very sensitive to magnetic fields, and so we have to shield it from sort of the Earth's field and any kind of noise in the environment. So that's the basic idea of what I did in my PhD. And now I want to give you a flavor of kind of where are these sorts of experiments going. So if you follow me on this treasure map, we always start on what I call spectroscopy shore. No one has characterized these molecules to the extent that we want to for the experiments that we want to perform. And so often you have to do laser spectroscopy to learn about the structure of the molecules, like what we did in our experiment. Then, once you know about the molecules, you can study them in a molecular beam. And in these beams, you have about a millisecond to kind of probe the molecules as they fly through your lab. And you can learn a lot about sort of physics in this way. In fact, experiments so far have really probed down and not found any deviation in the electron's shape from a perfect sphere yet. But there's actually a lot of room to go. And we think that we can make it by trapping and cooling the molecules. Now finally, after we trap these molecules, we can start thinking of what I like to call the quantum information jungle. Now you may have been seeing in the news recently claims of building a quantum computer, and this is kind of this field of quantum information that tries to understand how to use quantum mechanics to process information in a more efficient way. And people are starting to think about using molecules for these applications as well. And it turns out that we think you can use these sort of techniques of quantum information and quantum entanglement to make your measurements of new physics inside these molecules better. And that takes me to the X on the map, which is the land of quantum-enhanced searches for new physics. So once again, all we want to do is study the behavior of these electrons inside these molecules. But with quantum mechanics, we can actually engineer sort of measurements that are more sensitive than we could ever sort of get classically. We can use our understanding of quantum information and quantum entanglement to make our measurements as good as they can possibly be, and that will allow us to get to the next generation of sensitivity to really answer the question, where did the imbalance come from? How did we get here? And can we find the answers by looking inside these spinning molecules? Now, with that, I'd like to thank everybody who's been a part of my journey here at Caltech. This is a picture of my group. The group is run by Nick Hutzler, my PI. I want to thank all of our collaborators, particularly the Doyle Group at Harvard. And I also want to thank all of the opportunities I've had here at Caltech to do science outreach, particularly through the Center for Teaching, Learning, and Outreach. And finally, I want to thank the funders and also, of course, the cats that I live with.